And ooh, it's making a transcript of what I'm saying. That's pretty cool. Okay, so yeah, so I was telling Caroline before you got here. So I made up this Google Jamboard, and I've got a whole bunch of questions from the stuff that we were talking about the week before this one in class. So I've got stuff about continental drift and plate tectonics, and then about the Earth's interior, and about earthquakes and tsunamis. For both of you, is there anything specific that you want to start on? Or are there like any questions that you had? Or do you want to just like go through all of the stuff? All of it? Sounds good to me. Okay, I'll put that over there so I can always see the chat too. And oh, and what I'll do is I'll share my Jamboard so it shows up on the recording. But feel free to like open up the Jamboard yourself too, and then you can like draw on it, type stuff on it. Hopefully it should work pretty well. Okay, so I want to start with the first question I got on here on the second page of the Jamboard. So the question says, Alfred, I think it's pronounced Wegener, Alfred Wegener proposed the continental drift hypothesis. So what was his evidence? So do either of you remember what sort of things that Alfred saw that made him come up with continental drift? And yeah, if you got any ideas, you can either say it over the microphone or put it in the chat, whatever you're most comfortable with. Continents fit together like a jigsaw. That is a really good one. If you want to, you can put them right in the Jamboard, but totally up to you. Fossil evidence. That's a really good one too. Yeah, so we got continents fit together really well. So especially if you look at the continental shelves of like South America and Africa, they fit right together, which made him go, huh, maybe there used to be like something together here. Fossil evidence from animals that wouldn't have been able to swim. That's a really good one. How did the animals get from this side to that side? So I'll throw that in. Fossil evidence. Some other ones I can think of, the top of my head super quick. We've got similar rock types being found on different continents. I feel like there's one more, but I am not remembering what it is right now. Got continents fit together, fossil evidence. Oh, I see Amy's typing something. Oh, yeah, that's a really good one. Yeah, so we have things like indicators of climate in fossils and in rocks that say like, hey, maybe this really tropical area had evidence of glaciers, or vice versa. So you have evidence like that stuff has moved. So we have like climate indicators in the wrong spots. And then the one other that I want to bring up that we're going to talk about on the next slide is rocks holding evidence about magnetic fields that don't seem to line up in the right spots. So, okay, so, oh, and the other question I want to ask before we go on to the next slide was, why wasn't Wegener's hypothesis accepted while he was alive? What was the big problem that all the other geologists had with it at the time? I guess there might have been a few problems too. And a few reasons why they didn't accept it, but there was one like big problem with the continental drift hypothesis. Yeah, that's exactly it. So there's no mechanism. Like, he's just saying, hey, looks like the continents used to be together, but like, I have no idea how North America got from over here to over here. Yeah. So, okay, so I want to go on to the next page. So I'm on slide number 3 of the Jamboard. And I want to go through a whole bunch of questions on magnetic fields. So the first one I've got is, what causes the Earth's magnetic field? So, do either of you have any ideas? Remember anything from the lecture? What makes the Earth actually have a magnetic field? And you can feel free to like type it in the chat, say it out loud if you're comfortable. You can put a sticky note on the Jamboard. If you go over to the left side of the Jamboard, there's like a button with a sticky note. But whatever works for you. So, oh, I'll give you a minute to finish typing. Is it the decay of radioactive isotopes? And one other thing. Radioactive isotopes, I don't know. Yeah, I don't think radioactive isotopes have anything to do with the magnetic field. But that's a really good guess. And that is, yeah, like you said with heat, that is one of the sources of where Earth's heat from within comes from. So radioactive decay produces heat, and that heat gets transferred up towards the surface of the Earth. Earth's iron core, that is the big driver of Earth's magnetic field. And the really important thing about Earth's magnetic or Earth's iron core is that if you remember when we're thinking about the core, the Earth has an inner core and then it has an outer core. And the inner core is solid, but the outer core is liquid iron and nickel. And it's that movement of the liquid iron nickel outer core that's moving in all these like crazy funky convection currents around the inner solid core. And that's what causes the Earth's magnetic field. So it's all about that movement of the outer core over the inner core. So that's what causes the Earth's magnetic field. And then the next question I've got there is, what are magnetic inclination and declination? So one of those two things has to do with a compass and which direction it points. And one of those two things has to do with if you have a device called a tilt meter, how horizontal or vertical it'll be. Do either of you have a guess which one is which? Which one inclination would be or which one declination would be? And so also totally fine if you have no idea. Not sure. Okay. So when we're talking about magnetic inclination, that's like a compass direction. So like which way is pointing towards north? And then when we're talking about magnetic declination, that has to do with something called a tilt meter, and how horizontal it would measure. So I want to draw a little bit of a picture here. I'm just going to move my diagram there out of the way. So if we're thinking about this as the Earth, and we've got our North Pole up here and our South Pole down here, if we're thinking about Earth's magnetic field, and we were going to draw some magnetic field lines on here, they kind of go like this, connecting up the North Pole and the South Pole. And then rocks that have formed on the Earth's surface, when igneous rocks cool from magma and become solid, they're able to trap clues about the magnetic inclination and declination wherever they are inside of that rock by the way that certain magnetic minerals are pointing. So that sounds a bit weird. Like, do you remember that from class? Or is this like, I have no idea what you're talking about? Okay, sweet. I'm not making stuff up. So if we had a piece of rock that was right here, where I just put my green dot, so that piece of rock, if we were going to look at the declination in that rock, it would be lining up with the field lines at this point. And so it would be like parallel to the Earth's surface at that point, or horizontal. And then if we were going to look at a piece of rock up here by the North Pole, the magnetic declination that's stored in that piece of rock would be really vertical, because all the field lines are coming in and like pointing right down towards the North Pole. Does that make sense, or is this like totally, I have no idea what's going on? I'm not doing a great job of explaining it. Okay, kind of makes sense. Okay. So, that sort of brings me to, do you say that magnetic inclination is vertical and declination is horizontal? Okay, so magnetic inclination would be like if I don't actually have a piece of rock here, but maybe if this speaker was my piece of rock, and I don't think that's gonna help explain it very much. So the magnetic inclination is gonna be like the compass direction. So you can look at the magnetic inclination in a rock, and it's gonna be pointing towards where the North Pole is. So I guess it would be kind of like, if this was my piece of rock, the magnetic inclination would be like an arrow on top of it. Oh, okay, yeah. And then magnetic declination would be kind of like I drew in the diagram of the Earth with the field lines. And it would be like some amount of tilt according to what those field lines are. Okay, sweet. Yeah, so they're kind of weird, but they are two different things. And I guess that's the important part. So my third question on there is, what's the Curie point? So do either of you remember hearing about the Curie point in class? Do you remember what it is? No idea? Remember hearing about it? Okay, so the Curie point is the temperature at which a magma or a lava is cooling when it locks in whatever the magnetic inclination and declination at that point on the Earth is. So if we're thinking about like magma that's cooling into an igneous rock, so it's liquid magma, it doesn't have any sort of like magnetic indicators in it. And it's liquid magnet, it's cooling. All the atoms in it are starting to move around slower and slower. And then at a certain temperature, when it hits their Curie point, all of those, all the atoms in the magnetic minerals are going to lock in their position. And so after that, if the magnetic field on the Earth was going to change for some reason, it would still be pointing the same way. It wouldn't change with it. So that's what the Curie point is. So it's like when a cooling magma that's turning into a rock locks in the magnetic inclination and declination. So I want to sort of take a look at this diagram I got going on here. I'm going to erase my Earth so you can actually see it. So I've got a big cross section of some land, and there's like a person, a house, and a tree on the top. And then underneath that, there's all these different layers of rock. And so on the left side, I've got the magnetic inclination. Or sorry, on the left side I've got, on the left side I've got the magnetic inclination. And on the right side, I've got the magnetic declination. And so what I want you to try to figure out is, has this spot of land been moving closer to a pole, or has it been moving towards an equator, to the equator over time? And I'm going to actually put my diagram back in, because I think it might help. This is Earth's magnetic field lines. I'm going to give you a hint too. Don't even look at the magnetic inclination. Just look at the declination. So I've got a little drawing of the tilt meter for each of those different rock layers that have locked in that magnetic declination. And so in the older ones, the declination is really vertical. And in the newer ones, it's been going more and more horizontal. So do you guys have any guesses? Do you think it's been moving towards a pole over time? Or do you think it's been moving towards the equator? Or do you have absolutely no idea? And it's kind of tricky, so no worries if you're not sure. Not sure. Okay, that's totally fair. It's a tricky question. So, okay, so I want to look at the oldest layer first. So in that oldest layer rock at the bottom, the tilt meter is showing that the magnetic declination is really vertical, like it's nearly straight up. So if we're thinking about a spot on the Earth where the magnetic declination is going to be really vertical, it would have to be right near a pole. Because those magnetic field lines, that's a spot where they go really vertical, when they're like coming into the pole. And then if we look up at the newest layers of rock, where the magnetic declination is getting more horizontal, if we're looking at my little diagram up top here, that's going to be closer to the equator. Because right here, when we're close to the equator, the magnetic field lines are really horizontal, or like almost parallel to the surface of the Earth. So this piece of land has been moving from one of the poles towards the equator. So does that make sense, or is that still really confusing? Because it could be really confusing. Okay, sweet. So the last question on this slide before I want to move on is, what is polar wander? So do either of you remember like hearing about polar wander in class, or like seeing it on Cliff's slideshows? Yeah. Do you happen to remember what it is? So polar wander. Oh, I'll give you a minute to type there. Is when the continents drift and it seems like the poles are moving. Yeah, that's exactly it. So okay, so that would be yeah, so when the continents drift and it seems like the poles are moving, if you don't know they're drifting, that's what we like to call, that's what we call apparent polar wander. So I remember there's a diagram in Cliff Slides where it looks like maybe like the pole should be moving like this, and it's actually moving up like that. So yeah, so the Earth's poles do sort of like drift around over time. So I remember when I was in elementary school, the North Pole was somewhere over Baffin Island, and I have no idea where it is right now. But the Earth's North and South poles do kind of like drift around, just sort of slightly over time. And then a pole apparent wander, just like you said, is if you're looking at all the magnetic declination and inclination records in rocks, and you're looking at it, it's going to look like the poles are wandering a lot more than they actually are, if you don't know that the continents are moving too. Okay, so that's a whole bunch of magnetic field stuff. Do you have any more questions about like any kind of magnetic field stuff that we didn't cover, or any stuff that's confusing? Okay, so we can move on to the next page. And this, I just want to go through this one super quick, and then we can move on to some more stuff. So I've got, what would you see if you pulled a magnetometer, so an instrument that measures magnetic fields, across the Atlantic Ocean? So I'm going to draw in. We've got one side of the Atlantic Ocean, got another side of the Atlantic Ocean. We got water. And then I'm going to draw on the sea floor. And we're going to see some mountains in here. But do you remember what sort of thing we're going to notice along the seafloor in the Atlantic Ocean? Or do you have any guesses? And this was the thing that turned Alfred Wegener's hypothesis into the like currently accepted theory of plate tectonics, if that helps. So this is like a super big discovery. Seafloor spreading. So that is the big thing that made everyone go like, whoa, this is actually happening. Like the continents are moving apart. Do you remember what it was on the ocean floor that actually showed that seafloor spreading was happening? Yeah, so seafloor spreading is like one really big part of the puzzle that came together. Valleys. I'm not exactly sure what you mean about valleys there. We do find, so one big thing that people did find was these giant mountains at the middle of the Atlantic Ocean. So that's kind of interesting. And then the other really big thing that people found was if you take a magnetometer, so the scientific instrument that can measure the magnetic fields in rocks, they noticed all of these stripes where it was kind of like maybe in the black sections here, the magnetic inclination in the rocks was all saying north is this direction. And in the white sections there, all the rocks were saying, hey, north is actually this direction. So it's like there were these alternating stripes. And they're mirrored on both sides of those big mountains in the middle. Does that sound kind of familiar? Or is this like totally new stuff? Okay, yeah. So, and then so this shows that seafloor spreading was happening. So over Earth's history, we know that Earth's magnetic field has flip-flopped back and forth. So the poles like to kind of wander around a little bit over time, but like once maybe every few million years, the Earth's poles will just flip. So this used to be North Pole, this used to be South Pole, and then now this is the South Pole and this is the North Pole. And then they flip again and again and again. And we don't know why they do that, but that does show us that if we have these bands that are alternating back and forth of the magnetic inclination, it shows us that over time, the seafloor must have been spreading because this band right here formed when north was that way, and then the one next to it formed when north was that way, and the one next to it when it was that way, and that way. So those stripes show us that the seafloor is spreading. And then that shows us that the continents must have been moving. So, okay, on the next page, I've got a big grid. And I really like drawing out this grid, but it does take a little bit of time. So you might miss some questions at the end. So how do you both feel about plate boundaries? Do you want to go through all the different plate boundaries, or do you think you got those kind of covered? Because it's totally up to you. Because we can do these, we can do that grid question about plate boundaries. Or we can make sure we have time for some more like earthquake and tsunami stuff at the end. Okay. If you don't have a preference, I want to do this question on page number 5. So, okay, so on page number 5, the Jamboard here, I've got this 3x3 grid, and it's got 1, 2, 3, 4, 5, 6, 7 squares on it, because 2 of them are grayed out. And so along the top, I've got different types of plate boundaries in that, like, is it a continental plate boundary where two pieces of continental crust are coming together, moving apart, or going side by side? Is it an oceanic boundary? Or is it an oceanic continental boundary? And then on the left side of the grid, I've got different types of plate boundaries in the way of, like, is it a convergent plate boundary where plates are coming together? Is it a divergent plate boundary in the way that plates are coming apart? Or is it a lateral plate boundary where plates are going side by side? And what I want to try to do is I want to have us all draw in pictures of all the different plate boundaries in this grid. So, first of all, can you guys actually, like, draw on the Jamboard? Because I know sometimes I make them and people can't actually draw on them. Because I forgot to, like, set it to editable. Oh, I see whoever is Anonymous Pumpkin can draw on it. Perfect. Whoever is Anonymous Turtle, are you able to draw on it? Perfect. Okay. So, what I want to do is I want everyone to, like, grab a box. So I'm gonna do them too. So I'm gonna grab the I'm gonna grab the convergent oceanic continental box right here, and I'm gonna, like, draw a picture of what that plate boundary kind of looks like. I want both of you to pick a box too, and you can start drawing a picture in that. And when you're done, you can just move on to another box. And hopefully in a few minutes, we should have, like, a filled up grid. So if you got any questions, you can let me know. But I'm going to start drawing. And it doesn't have to be a beautiful picture too. It's kind of hard to draw with the mouse sometimes. Oh, and if you want to make it a bit easier to draw too, in the top left corner of the, like, Jamboard website, there's a little zoom thing, and so you can go to that and you can make it bigger to make it easier to draw on, if that helps. So I'm going to start with oceanic, continental, and convergent. And if you have, like, no idea what to do, let me know too. Because I'm zoomed in on my box and I can't see you. So it's going to be oceanic, continental, a convergent boundary. Got two. Awesome, we got some nice pictures coming together. I'm gonna pick another one too. I'm gonna go for continental, continental, lateral. And I'm going to grab oceanic convergent. Anyone wants to take a shot at oceanic lateral, you can do that. Or I'll get it if nobody's, if you're not sure. So yeah, oceanic. Poop. Poop. Okay, and I'll draw in a quick picture for oceanic lateral. Actually, it's going to be the same picture as this one, so I'll draw an arrow. Okay, so we got this whole grid filled in now. So I just want to like go through a couple of them super quick. So I'm going to start with I'm going to start with the top left corner up here. So continental, lateral. So that's when you get a plate boundary where you've got two pieces of continental crust that are going past each other slideways, but they're not coming towards each other or apart from each other. If you were going to think about a place where you might find this kind of boundary, you could think about like the west coast of North America. So if you're thinking about like the San Andreas Fault, you get a bunch of earthquakes because of that. There was a movie about it with Dwayne Johnson in it. That's all caused by a continental lateral boundary. And then an oceanic continental lateral boundary is going to be the same thing. You're going to have two pieces of oceanic crust that are sort of going past each other. But if you were going to think about a place where you really see this, you would probably want to think about like in the middle of the Atlantic Ocean. So if you think about the middle of the Atlantic Ocean, where you've got plates that are spreading apart away from each other, it looks like it's also got, so I'll draw a diagram here. You've got plates that are moving away from each other. You've also got all these like cracks, they kind of look like, along it that are going perpendicular to the direction they're spreading apart. And they're actually sort of connecting up where it's spreading apart, kind of like that. And all those cracks are places where you got oceanic crust that are going sideways next to other oceanic crust. So for the next row here, we've got continental divergent boundaries. So we've got two continental plates that are coming apart from each other. And then, yeah, that looks pretty good to me. And then right in the middle, I think you were drawing this in as well. So in the middle of that boundary, we tend to have big like rift valleys. So I'm going to add a little bit in, kind of like that. And we get these valleys where it's sort of like as the plates are pulling themselves apart, it's kind of like pieces of land are like falling down into those valleys to sort of like fill up the gap. That's the way I always sort of visualize it. And then we can go to the oceanic divergent boundaries. And yeah, and so we've got like big mountain being drawn here. Plates are spreading away from it. So that big mountain could be like the Mid-Atlantic Ridge. That looks pretty good to me. And then we've got our continental convergent boundaries. The one thing I want to make a little bit of a change with this diagram It's really good because you got plates that are coming together. The one thing I want to change is that when you've got continental plates and continental plates converging, both plates are like really thick and neither of them are very dense. So they don't actually subduct and have one going under the other, like you would find with an oceanic plate. But what they do more is they kind of like bunch up where they're colliding, and they make these big mountains. And if you remember from when Cliff was talking about the Himalayas that were formed when the continent of India collided with the continent of Asia, they also have these really thick like mountain roots of crust underneath them. So they sort of do that big like bunching up of continental crust. So that's convergent continental. And then we've got a convergent oceanic boundary here. So we've got oceanic plates can be subducted because they're really thin and they're really dense. So they're heavy. They kind of want to be pulled down. So whichever plate is the denser one, that oceanic crust is going to get subducted down into the earth. And then as it's going like into the earth, into the hot mantle, whatever like sediments and water and stuff that sort of gets like dragged down with it, that stuff can start to melt, and we get magma, and then that forms volcanoes. Kind of like, and those volcanoes, if they're tall enough, they can form volcanic islands, kind of like the island of Japan is a really good example of volcanic arcs created by a convergent oceanic boundary. No, sorry, I was wrong about that. That would actually be no, never mind. Yeah, so Japan would be a really good example of that. And then the last one at the end of our grid here is we've got a convergent continental oceanic plate boundary. So the oceanic plate is really thin and dense. The continental plate is really thick and not so dense. So when they come together, the oceanic plate is going to get subducted and pushed under. And then the same thing is going to happen. All that like water and sediment and crud that's getting subducted down with it is going to get melted, and that can form a volcanic arc on land. So that was a whole bunch of stuff. Do you guys have any questions about like any of that? Like, was there anything that didn't make any sense at all? Is there any drawing that you're like, oh, but shouldn't I have this as well? Any sort of, or are you like completely lost? Like, I have no idea what we just talked about. I'm hoping that's good good silence, not I've run away from my computer because I have no idea what's going on silence. So we've got 15 minutes left. I want to go through a whole bunch of other questions. On the next page, I had a map. This sometimes, like if you're going back and studying plate boundaries, I find it's really helpful to look at like a world map, especially one with the ocean floor. And you can think about like, where in the world would I see these boundaries? So like, what's all that mountain stuff going on at the middle of the Atlantic? What's going on there? And like, what's the big ridge up by Alaska? So that's why I've got that on there. But I want to go to page number 7. So the question I've got here is, what are the 3 processes that drive plate tectonics? So like, what is it that actually makes the continents move? So do either of you guys have any ideas? Do you remember any of this from in class? I have no idea. No idea. Okay. That's absolutely all right. So, if we're thinking about three things that make plates move, so one really big one is is convection. So, do you remember what convection is? Or is this like new word? I have no idea. So do you remember Cliff in class talking about, so convection currents are when you have in the Earth's asthenosphere, the part of the Earth that is really flowy. I'm going to draw a picture here. So this bottom part here is the asthenosphere, the part of the Earth that's really flowy. It's really hot. And the rock in it is kind of like Play-Doh. It can like move and flow around. And it forms these convection currents that go like this. So because they're really hot on the bottom, but a lot cooler on the top, the rock sort of moves around in these big like circular currents. Does that sound familiar, or is this like totally new? Okay, perfect. So these convection currents that are going on in the Earth's asthenosphere, they're able to actually push plates apart. It's like right here, we'd have a spot where the Earth's plates are being pushed apart because of those currents. And like over here, and if I draw another current in here, this would be a spot where we've got plates that are being pushed together because the currents are pushing them the other way. And then the other two big things are called ridge. I always get these backwards. Ridge push and slab pull. So do either of you remember Cliff talking about these in class? Because I don't remember if he actually mentioned them. So if he did, I want to talk about them. But if he didn't, just know they exist. Don't remember it. Okay. I'm going to leave those on there then. And they're definitely in the textbook. So if you like get asked that on a quiz and you need to figure it out, I'm sure it's in there. But if he didn't go through it in class, then I'll just leave that like that for now. So I want to go to the next page. So the question I've got here is, what are hotspots? And sort of go along with that, why are there all of these sort of like linear island chains and seamount chains in the Pacific Ocean? So do either of you remember anything about these like hotspots? Or do you remember why the Hawaiian Islands exist? Or you're like, oh, I kind of remember, but not really sure. Does it have to do with aftershocks of earthquakes? That's a really good guess, but it wouldn't be connected to this. But that's a really good guess. So, so a hotspot is a volcanic island or a seamount, kind of like an island that is below the surface, that's been formed because magma is coming up from the Earth's mantle. But the really important thing about hotspots is that they're not along plate boundaries. So if you think back to the grid that we made a few minutes ago, where we had volcanoes and volcanic islands forming at those oceanic, and oceanic continental convergent boundaries. So those are totally different. These are when we have magma that's rising up from the Earth's mantle, but not along a plate boundary, right in the middle of a plate. So if you think about the Hawaiian Islands, they're right in the middle of the Pacific Ocean. There's no plate boundaries around. And so we know that it's magma that's coming up from the Earth's mantle. And as the oceanic plates move around over top of them, they tend to just like stay in place as the crust moves. And that's why they form these long chains. And we don't really know why they happen, but we know they exist because we have things like the Hawaiian Islands. So that's hotspot stuff. We've got like 6 minutes left. And I want to skip ahead to page number 10 here. And so on page number 10, I've got a question that says, what are the 4 different types of seismic waves or earthquake waves? So does anyone remember any types of waves? Love waves, yeah. We've got love waves. I'm going to throw that down here. Rayleigh waves, that's another really good one. And I'm going to add on that these are both surface waves. And then P waves and S waves. Perfect. Got P waves and S waves. And so do you guys want to go through the different types of waves? Or do you want to move on to the next question? Because it is super important to know the difference between them. But if you already got that, we can get a couple more questions in. What are you thinking? Okay. Amy says she's good. I'm going to move on to the next question. So, I want to skip ahead a little bit to... Okay, I want to skip ahead to page 12, because I think it's the last, like, really important thing I want to do. So on page 12, I've got the question, what are shadow zones? And I've got these 2 pictures of a planet that could be kind of like the Earth. And I've got a star right at the top of each one. And so that star is going to be the epicenter of an earthquake that just happened. And then inside the planets, I've got this area is sort of like the asthenosphere. Or this area is sort of like the mantle, I should say, actually. And then we've got an outer core that's liquid, and we've got an inner core that's solid. And so what I want to try to do is I'm going to draw in P waves on one and S waves on the other. So I'm going to put P waves over here, and I'm going to put S waves over here on this one. And so I'm going to start drawing on here. So if we had an earthquake, and then our P waves are going to start to move through the Earth away from wherever that earthquake happened. So they're going to do something kind of like this. And they're going to spread out through the Earth. And they're going to reach the surface at different spots. Does this type of diagram sort of seem familiar? Like, do you remember seeing something like this in class? So we've got P waves spreading through the Earth. Do you remember it from class? Perfect. And then our P waves, those are the waves that are going, and it's like rock particles hit other rock particles and push them ahead. So the P waves are like forward movement, forward waves. And P waves can travel through liquids. So our P waves are going to be able to go through the Earth's liquid outer core. And when they do that, they're going to do this sort of weird refraction thing. But they are actually going to be able to go through it. I'm going to draw a bunch more arrows on here. And what's going to happen, though, is our waves are going to be able to reach all around the Earth, except for these sections here. We're going to have barely any P waves hitting at those spots. And so those are going to be our P wave shadow zones. And then for our S waves, we're going to have the same sort of thing going on, where the waves are propagating through the Earth, moving away from the epicenter. For our S waves, those are the waves that are moving, the particles are moving perpendicular to the way the wave is going. They kind of look like really wavy if they're traveling that way. Our S waves can't go through water, or sorry, they can't go through liquids. So they're not going to be able to go through the Earth's outer core. And then we're going to get a big shadow zone all the way along the back side of the Earth from wherever the earthquake is. And so there's going to be no S waves that are going to be able to reach there. And we're going to have an S wave shadow zone. And the really important thing about those is that that's how geologists found out a lot of their information about the interior of the Earth. So that's why we know that the outer core is liquid and this inner core is solid, because we're able to look at all kinds of earthquake data and look at where those shadow zones are and how the waves are being refracted and diffracted and reflected. And then we're able to make a model of the Earth and figure out where the inner core is and where the outer core is. So it's 7:01, so I don't want to hold you both. But if you got any more questions, you can let me know. I put on the last page of the Jamboard too, I have a form for feedback. If there's anything that was really helpful, anything not super helpful, anything else you want to say, all feedback is appreciated. And thanks so much for logging on tonight. So I'll stick around for a minute if you got any questions. But have a great rest of your evening. You're welcome. Thank you for coming.